Hello students, today we are going to see chapter number 3, processes. The topics that I will be covering today is process concept, process scheduling and operations on process. The process is a program that is in execution. Program that is written in high level language is saved on the system as a file. But this file or a program only gets executed when you instruct the operating system to execute it. The program, when it is executing, it is a process. Hence, a program is called a passive entity and a process is called an active entity. Process execution must progress in sequential fashion. That is, instruction by instruction, each instruction has to get executed till the end of the execution. For this, the operating system allocates certain resources. The resources can be like memory, the main memory, the CPU and the I/O devices if required. So, in memory, the process takes up the memory in multiple parts. That is, whatever memory is allocated in the RAM, it is divided into sections called as text section, program counter, stack, data section and heap. A text section is a section where the actual program code resides. It is from where your instructions are fetched for execution. Next we have program counter. It is the counter which keeps track of which instruction is getting executed and hence also notifies which is the next instruction to be fetched from the main memory for execution. Next we have stack. Stack contains temporary data. It contains information about local variables, which function has called which other function, and at the end of that function execution, which instruction of the called function has to execute. So all this is stored in a stack. Next we have data section. A data section contains the global variables. Whatever program global variables are there are stored in this section. Next is heap. Heap is from where your program dynamically allocates memory to any variable, that is any variable or any section that requires the dynamic or runtime memory. So this is how the memory is divided into sections. So from a 0 is not actually the location of memory RAM, but it is the initial memory location to the maximum memory location that your system requires. So here your 0 indicates the beginning address of the program and max indicates the maximum memory required by this program. This memory takes the text memory, the data memory, heap. This arrows indicate that this memory can reduce or increase. Then there is stack. Next we have process states. Process states. A process executes in different states. These states are new, running, waiting, ready, terminated. So a new is the process when it is just begin its execution. That is when you have asked the operating system to execute the program. That is, the process is in new state. The process is in running state when its instructions are being executed by the CPU. So it is running in that state. Next is waiting. A process is in waiting state when there is some I/O request or when there is an interrupt occurred. So it goes into a waiting state. Next we have the ready. Ready state is a state when the process is waiting for the CPU's attention. As a CPU has to execute multiple processes simultaneously one after the other, there is a queue that is maintaining these processes in a queue so that the CPU is allocated one after the other the process for execution. Next is terminated. Of course, when the program finishes its execution, the program terminates. So that is terminate state. So this can be seen through this diagram. So here we have a new wherein the process execution starts when you ask the operating system to execute that process. So that is when the process gets admitted into your ready state. So in the ready state, the process is waiting for the CPU's time. This CPU is allocated through a scheduler dispatch. So the scheduler dispatcher picks one program from the ready queue and provides it to the CPU for execution, and that is when the process goes into running state. During the process execution in the running state, the process can get an IO or an event request. In that case, the process is put into waiting state, and then it goes into an IO or an event completion and comes back into ready state. If not an IO, the program can be interrupted by an interrupt, and hence it will come back to the ready queue when it is interrupted by an interrupt or a system call. So again, it gets scheduler dispatcher has to select that process, put into running state, and then when it finishes, it goes into the terminated state. So this is how your process gets executed in the system. For the process to get executed in the system, we need to know different information about a process. To store this information, the operating system maintains a process control block, that is in short called PCB. A process control block contains process state information, it contains the process number, it contains program counter, registers, memory limits, list of open files. Apart from this, it contains some additional information. Let's look each of them one by one. Information associated with each process, also called as task control block. In general, it is called process control block. Very rarely, it is called task control block. Process state. The process state can be running, waiting, ready, and so on. That is the one which we previously saw in the previous slide. Next, we have program counter. As I told you, it contains the information of which instruction is getting executed or instruction to next execute. So it contains actually the location of the instruction. So this is stored in your program counter. Next we have CPU registers. The CPU registers contains information of what data is stored in the CPU register while the program was in execution state or in running state. So you already know that the CPU has 32 registers, and in these registers we keep the information that we want to keep in handy when the CPU wants to execute the instructions. So the data that is required by the CPU for execution is stored in registers. So this contents of the CPU centric registers information is stored in this registers section. Next we have CPU scheduling information. CPU scheduling means the process that is picked for execution by the CPU is decided by a CPU scheduling. This CPU scheduling can be done either by priority, that means higher processes get executed first, lower processes get executed later. So in this way we have the process scheduling, and for this we need. Next is memory management information. Memory allocated to the process is stored in this information. Accounting information, we get the CPU used, clock elapsed time since start, time limits, etc. What is this? CPU used means how much processing is done. Clock time elapsed since start. It indicates how much time has been spent in processing this particular process, and time limits indicate that how much time it should end probably. So if it doesn't end within that time limits, then the operating system will show a message, an error message, that the program is not responding. That's how you get the message or the warning. Do you want to close or do you want to wait? So this is useful there. Next is I/O state information. This indicates the I/O devices allocated to the process, list of open files that are used by this process. Next, we will study the CPU switch from one process to another process. Supposing process P0 is running. So here you can see that P0 is getting executed. It's in running state. So at this point, supposing an interrupt or a system call comes from process P1. So in that case, the operating system will save the state into PCB0. What is PCB? Process control block. So this is the process control block for process 0. The 0 here indicates process control block for process 0. So it will do a certain set of activities before it loads the next process, that is the process control block for process 1. Once it loads the information, so where is this information getting loaded? So this information will be there in the ready queue. From the ready queue, the PCB information is fetched and loaded in the CPU. That is, the program counter will be updated with the instruction that needs to be executed. The registers will be updated with the data, and stack and other information will be fetched for execution. Once that is done, once this reloading of information is done, the process P1 will be assigned to CPU for execution, and hence process P1 starts its execution process. Once this gets an interrupt from some other process, PCB1 will be updated with the current information of the executing process, and it will save this information into PCB, and it will go in to take up the other process. Now again it has come back to process P0 because it is loading PCB of 0 information into the system. So once that is done, process 0 will continue its execution. So at this time, when there is switching between processes, P0 was idle till again it was reloaded and the CPU was assigned to it. And when P0 was executing and the operating system was doing all the task of changing the system information, P1 was in idle state. So when again P1 was executing, P0 is in idle state. Then again there was a switching from P1 to P0. At that time, there also both were idle. So in this case, we come to know that at a time the CPU is processing only one program. But the switching between the processes is so quick that we feel that multiple programs are being executed by the CPU simultaneously. But actually, only one process is getting executed at a time. Let's see threads. What are threads? We have understood process. A process is a program that is in execution. This is it is called heavyweight because it is allocated memory and resources, and it is having a dedicated memory space, and all the process related information is updated and kept. But whereas threads is a lightweight. So what do you mean by lightweight? Lightweight means threads do not get memory allocated separately, resources allocated separately. Whatever process, whatever memory and resources is allocated to the process, that is shared by all the threads of that process. That means a single process can have n number of threads running. What does this mean? Let me explain threads with an example. Now, word processing is what we use regularly. But in word processing, when we are typing the content or a document, at the same time, there is spell check running, formatting running. So, this is done because there are multiple threads that is taking care of this documentation. How is this happens? One thread is taking care of the spell checks. So as we type, if we do a spelling mistake, it automatically corrects that spelling. On the other hand, if there is any formatting or grammatical errors, it highlights those errors. So if we have, for example, we put a full stop and start the next statement with a lowercase alphabet, then automatically it converts it to uppercase. The first character is uppercase. So this all is done because there are threads running simultaneously while we are typing, and it is recording the characters that we are typing. So there are thread which is noting down the input that we are sending it to the document. There is another thread which is taking care of spelling check. There is another thread which is taking care of the formatting. So this is what we call that a single process has multiple threads. So consider having multiple program counters per process. So threads have their some data, some information specific to each thread, but the main resources are shared. So we will study more about this in our multi-threading system in the next section of this unit. Next is process scheduling. So what is process scheduling? Process scheduling means since we have multiple processes running by the CPU, there is a ready queue in which there are multiple processes put, and each of these processes require CPU time. It should not happen that one process gets the CPU continuously and the other process keeps starving for the CPU. Hence, we need to keep a track that every process that is there in the ready queue should get the CPU time or attention to execute itself. That's why we say that the CPU needs to be shared by all the processes. For this, we need to take care that there is a quick switching between processes so that the CPU time is equally given to all the processes. So maximizing CPU use quickly by switching between processes is what is the task of process scheduling. So we need for this process scheduler. So process scheduler is the one who selects among available processes for the next execution of the CPU. So which process has to be executed next is decided by a process scheduler. So process scheduler also maintains certain queues. So it has to do this so that it knows which process has to be executed next. So a queuing system is used. So there are job queues, there is ready queue, there is device queues. All these are the different queues that are available in the system. So a job queue is a set of all processes in the system. So any process can be in any state, in any queue, but it is a job queue. Next you have a ready queue. A ready queue is a set of all processes residing in the main memory, ready and waiting for execution. So it means that this is a queue which is going to get these processes that are kept in this ready queue are the ones which are going to get the CPU time. Next is device queues. Device queues are basically the IO device waiting queues. For example, printer has its own waiting queue. So if you have already given a print command for one document and you give immediately before it ends another document print command, then this will be queued for the printing. So that is what is device queues. So like that you have device queues for your other device IO devices as well. Next you have process migrate among these various queues. So obvious it is that a ready queue From a ready queue, a process may go for a device IO request, so it will go into a device queue. Then after it finishes the device queue, it may come into waiting queue because there may not be a space in the ready queue. So it will come into waiting queue and then it may come back to ready queue. So all these are the different queues and we will be studying about them in detail further. This is a snapshot of the different queues that the device has. So if you see here, we have a ready queue and the ready queue has two PCBs. So PCB 7, that means process 7's control block and process 2's control block are present in this queue. So the head contains the block of the first process that is there in the list and the tail contains the last process in the list. This is like a linked list. So next we have magnetic tape 0 and magnetic tape 1 device queues. So these device queues do not have any processes waiting. So hence this list is empty. Next we have disk unit queue. Here also we have 3 processes that are in queue waiting for this disk space to be allocated. Next we have terminal unit. Terminal unit we can consider it as a display. So this is the display unit queue which has one process which is waiting for the display to be provided. Next is representation of process scheduling. So if you see in the system, this is how your scheduler works. A process enters into a ready queue when it is ready to execute. When you give it a command to execute, the operating system gets a program execution instruction, it puts it into the ready queue. From the ready queue, one by one, the processes are allocated to the CPU for execution. If the process finishes its execution, then it gets terminated. So this arrow indicates that the process is going out of the system as it has finished its execution. If it has not finished its execution, then one of these 4 cases can arise. The first one is the IO request. That means the process requires some input or output process to be done. So it will go into an IO request and from the IO request it goes into that device's IO queue and then it gets that particular IO device's attention and it returns back to the ready queue. Next, it can also have a time slice expired. Now what is this time slice expired? The CPU time can be divided into quantums. Means the CPU's attention we want to give each process equal time of the CPU. So hence what we do is whatever is the number of processes available. Supposing there are 5 processes available and we say that the CPU's time is divided in time quantum of 4. That means 4 milliseconds the processor will be allocated to each process in the ready queue one after the other. Next, when this process quantum time, supposing process P1 gets CPU's attention for 4 milliseconds, then after 4 milliseconds, the time quantum gets expired and hence we say that the time slice has expired. Once the time slice has expired, the process is put back into ready queue. The other option, the other case may be that this process starts another process, a child process. We call it as fork a child. Fork a child means one process creating its child process. For example, when we download a file from the internet, we say open that file. We indicate the browser. From the browser's download list, we double click it and say open that file. So in that case, whichever file is downloaded, that particular file's software is loaded and that program is loaded into that program. So hence it is creating a new process. So it is called as that at that time the child process starts execution and it goes into the ready queue because it also requires CPU attention. The last case can be that a interrupt has occurred during the program execution, during the process execution. Hence, this interrupt will cause this process to go into a waiting state. So, the interrupt has to be processed by the CPU. Hence, the running process will be put into the ready queue back so that it gets the CPU attention. Next, we will discuss the schedulers. So, there are two types, actually three types of schedulers. Short-term scheduler, long-term scheduler, and one more, mid-term scheduler. Mid-term scheduler we'll study in the next slide. Right now we will look at what are short-term scheduler and long-term schedulers. Short-term scheduler is also called as a CPU scheduler. What does this do? It selects the processes that are ready for execution in the ready queue and it is allocated the CPU's attention. So sometimes this is the only scheduler available in the system. A short-term scheduler is invoked frequently in milliseconds of time or even faster. Long-term scheduler, on the other hand, is called as a job scheduler. This one selects a process that should be brought into the ready queue. That means I told you that the process are there in multiple places. Like for example, the process can be in a virtual memory. We will see what this virtual memory and all is there when we come to memory management unit. But right now you'll understand that if there is no space in the RAM for any program to be loaded, then and that program can wait for some times, we put that program into wait queue on a virtual memory. On a hard disk, there is a space dedicated for storing such kind of programs. This memory is called as an extended RAM. It is not actually the RAM but the virtual memory. Why is it called virtual memory? Because the main memories programs, when they cannot fit into the main memory, we put that into the disk, and this disk space is called as virtual memory because it is a virtual RAM. From there we pick the processes back to get into the RAM so that they can get executed when the processes that are kept in the ready queue terminate. As they end, they will leave the RAM and there will be space created for such waiting processes. So that is what is the job of a long-term scheduler, to get processes that are in other waiting queues to be got back to the ready queue. So getting processes back to the ready queue is what is the job of a long-term scheduler. A long-term scheduler is invoked infrequently and maybe it will be slow. Long-term scheduler controls the degree of multiprogramming. So how many programs you can keep in the RAM and execute to simultaneously the processes is called as degree of multiprogramming. Now these processes can be of two types. We can categorize these processes as two types, IO bound process and CPU bound process. IO bound process spends more time doing IO than computations. That means it is taking less of CPU time and more of the IO. So for example, if you are typing a document, then it is an IO bound process because it is interacting with the keyboard more than with the CPU. That's why it's called IO bound process. A CPU bound process spends more time doing computations. That means, like for example, a program, C program, which is having a lot of calculations and less of inputs, then we call it as a CPU because it takes more time of the CPU. So time slice that a process takes of the CPU is called as CPU bursts. So long-term scheduler strives for good process mix. So that means it should have, the processes should be equally IO bound processes and CPU bound processes. That is what is the main job of a long-term scheduler. Next, I have told you about mid-term scheduler. So mid-term scheduler can be added if the degree of multiprogramming needs to decrease. That means more programs are present in the system that need to be brought into the ready queue for execution. Then I told you that we will put these programs, if there is no space in the memory RAM, then we put these programs into virtual memory. So here is where the mid-term scheduler comes into picture. The mid-term scheduler is used to swap in and swap out the processes. So if you see in this diagram, from a ready queue, the process enters into the CPU. When it has to wait for something, then we put it back into the virtual memory. We put it into the partially executed swapped out processes, which actually is a virtual memory. From there, we swap it back to the ready queue as there is space created in the ready queue. This process CPU can also send for an IO waiting queue if the process requires input output, and then it goes into an IO and then comes back into the ready queue, as we have already seen this. And if it ends, if the process finishes its execution, then it goes to the terminate condition. That is end of the process.